Um, got it. All right. So I'll make this full screen. So I'll talk. Um, this is, I was told this is very informal.
Yes.
So please interrupt me at any time with questions or comments or suggestions. And I'll just plow ahead. So I'll just start with some definitions. So what are the objects of study? So this is something based on the paper that Mel put on the archive this past Sunday evening. So it's very fresh. And it's basically about looking at the zeros of a polynomial and its derivatives and how they can interact with each other. So let's give the definition. So we'll let f be a polynomial of degree n. And let's let lambda be some complex number. So for each j between 0 and n, we're going to let mu j be the multiplicity of lambda as a zero of the jth derivative. So the multiplicity of lambda as a root or a zero of the jth derivative fj. Okay, then we say that the derivative vector of f for this value lambda, so of f for lambda, is going to be written mf of lambda. And this is the n plus 1 tuple, mu 0, mu 1, up to mu n. Okay, so you can do this. And more generally, we can look at different values of lambda simultaneously. So if we let big lambda be an m tuple, lambda 1 through lambda n, lambda m, we can define the derivative array, which is just looking at all of these derivative vectors at the same time. So the m by n plus 1 derivative array is formed by making the ith row be mf of lambda. Okay, so this is the definition. And let me
you mean lambda I assume?
Yes, thank you. Lambda I.
I'm just proofreading a paper of mine, so I'm very precise. Normally
Okay,
I'm not.
Yeah, thank you. So here's an example which comes from Mel's paper. So if we take f of x to be equal to x to the fourth minus 4x cubed plus x, and then we take lambda to be the ordered pair 0, 1, then what is mf of this lambda? I'll just write down what it is. 1, 0, 1, 0, 0, and then 0, 0, 0, 1, 0. Right, so what this is telling us is that if we look in this first row here, this is recording when 0 is a root of f or its derivatives. Right, so 0 is a root of f, so we have of multiplicity 1, so that's where this little 1 is here. And then 0 is not a root of the derivative of f, so we have a 0 in the next entry. And then it turns out that 0 is a derivative, is a 0 of the second derivative of multiplicity 1, and so on. And so we just formed this array. And so Mel called this a multiplicity or a derivative matrix in his paper, but I'm going to call it an array because I don't want to call these things matrices unless we're multiplying them together or thinking of them as linear transformations, and I have not yet found an interpretation for this. Okay, so any questions about the definition before I move to a new page? Okay. So the sort of basic question is, what are these arrays? So which arrays appear as mf of lambda? So there are many ways one can construe this question. So you could ask, as you range over all f and lambda, what arrays appear? Or you could say, fix a choice of lambda, and then let f vary, and again, what arrays appear. And so we'll think a little bit about both of these. So this is sort of the guiding question. So here's a proposition, which is just another way to think about these multiplicity arrays, and this is due to Mel in his paper. So here it is. So let's let lambda be our complex number. and let f of x be a polynomial of this form. So a sum k going from 1 to n of ck times x minus lambda to the k. And I guess Cn is non-zero, so that we're actually degree n. So then mu k, so this is recorded, this is the multiplicity of lambda as a root of the kth derivative of f, is greater than 0 if and only if the corresponding coefficient ck is equal to 0. So for instance, when k equals 0, this is just telling you that lambda is a root of f if and only if there's no constant term here when we expand in powers of x minus lambda. So this is just an equivalent way to look at these multiplicity arrays. And we'll use this view a little bit later. So we're going to come back to this key question here and provide a quick partial answer, which was in I think the title of the talk that Mel wrote for me. So here's our definition. So let's say that the array, we'll take an array M, indexed Mij, where I ranges from 1 to m, and then j ranges from 0 to n, is called a multiplicity array. If it satisfies the following properties. So the first is that every entry should be a natural number. The second is that if you have some entry which is strictly positive, so if Mij is strictly bigger than 0, then j is strictly smaller than n, and the next entry, 1 to the right, has value 1 smaller. And the third is that if you sum the entries in the jth column, you should get at most n minus j. So the sum, I going from 1 to m, of Mij is at most n minus j for all j.
Are you going to motivate this definition?
So I'm going to motivate this definition by saying, I guess I can write it up here before I go to a new slide. So note, every derivative array is a multiplicity array. So another way to think about this is you look at these derivative arrays and you say sort of what are some immediate constraints on these arrays that come to mind? And you write those down. You say any array that satisfies these sort of obvious constraints, we're going to call a multiplicity array. So okay, this first condition is obvious, right? So you're looking at multiplicities of zeros. These have to be natural numbers. The second one is just saying that if you, I mean, this basically comes from the product rule, right? So if you have some lambda, which is a 0 of multiplicity, let's say r, then you take a derivative. It'll be a 0 of the derivative of multiplicity r minus 1. And then this third thing is just saying, well, the jth derivative of f has degree of f minus j. And so the total number of roots is going to be at most degree of f minus j. And degree of f here is just n. So these are sort of the three obvious constraints you come up with on what these derivative arrays could possibly be. Does that help?
Yes.
Yeah, so this is the motivation. And then the question, so this is a partial answer to the question up here. So every derivative array is a multiplicity array. And then the question is every multiplicity array a derivative array? So is this a necessary and sufficient condition or only a necessary condition for being a derivative array? Okay, so my next task is to answer that question negatively. So part 2 will be non-derivative arrays. So I want to give you a couple of examples of things that are multiplicity arrays but not derivative arrays to show that this necessary condition for being a derivative array is not sufficient. So here's the first example due to Mel. I guess it's in the new version of his paper, which should be on the archive. Okay, so let's let M be
on the archive tomorrow.
Or archive tomorrow. Okay, so let it be a 2 by n plus 1 multiplicity array such that the entries in the first column sum to n, the first column sum to n, okay, sum to n. So if m is not of the following form, and I'll write in a moment what it is, then M is not a derivative array for any choice of f and our tuple lambda. So what is the special form that we have to avoid here? Okay, it's where you have a minus 1 down to 1, and then the rest zeros, and then b minus 1, 1, the rest zeros, for some a plus b equal to n. So if I give you any other 2 by n plus 1 matrix, where the sum of the two things in the first column is equal to n, i.e. we sort of accounted for all the roots by telling you what's going on in the first column, then m has to have this special form. Otherwise, it can't possibly be a derivative array. And so the proof, right, so the proof is that if m is equal to mf of lambda, then f of x is equal to x minus lambda 1 to the a, x minus lambda 2 to the b, where a and b are just going to be these two entries, whatever they are. But then by direct computation, this forces the rest of the matrix M to look like this. So this is an example of, this gives a lot of examples of multiplicity arrays that are not derivative arrays. Okay, so that's one example. Another thing, which I haven't really been able to flesh out, which I think should be very useful, is this theorem, this GaussLuca theorem, which is very classical. So this is Gauss and Luca. I have no idea when it's from. And this just says that the roots of the derivative of f are contained in the convex hull of the roots of f itself. Of the roots of f. Okay, and so this immediately gives you a few ways to show that things are not derivative arrays. So here's one. Let me just, okay, so if lambda is equal to lambda 1, lambda 2, lambda 3 in increasing order, lambda 1 less than lambda 2 less than lambda 3, then this matrix M, 0, 1, 0, 0, 2, 1, 0, 0, 0, 0, 1, 0, is not a multiplicity, sorry, is not a derivative array for this choice of lambda. So you can see this satisfies all the other conditions for being a multiplicity array, right? So if you look across the columns, you're always decreasing by 1 unless you're at 0. And if you look at each row, or sorry, if you look in a row and you have a positive entry, then the next entry is one smaller than it. And if you look in a column, well, the sum is going to be at most n minus j in the jth column. But this is not a derivative array. So let me give you the proof. Okay, so suppose that M is a derivative array for lambda, so it's equal to mf of lambda for some f. So we know that two roots of f have to be lambda 2 and lambda 2 from this first entry here. Okay, so by GaussLuca, if we look at this second column here, we know that lambda 1 has to be in the convex hull of the roots of f. But then if we look in the second column, the third column, we see that lambda 3 also has to be in the convex hull of the roots of f. So by GaussLuca, we know that lambda 1 and lambda 3 are in the convex hull of the roots of f. But this is going to be clearly impossible. So here I'm drawing the real line. Here's lambda 1, lambda 2, and lambda 3. So we know that 2 of the roots are here at lambda 2. And because f is cubic, there's only one more root. But then you can't place this last root both to the right of lambda 3 and to the left of lambda 1. And so there's no way you can force lambda 1 and lambda 3 both to be in the convex hull of the roots of f. So this is impossible. So I think that it's probably also possible to prove directly using Descartes' rule of signs or something like that, that this matrix M is not going to be a derivative array. But this Gauss-Luca argument is certainly much shorter and simpler than anything else you'd have to do, like getting your hands really dirty with computations. Any questions about this? I can't really see that.
I think that you're already, I mean, the fact that you're talking convexity rather than just the rule of signs, you're going to have some corollaries for complex numbers that would be very hard to prove using the rule of signs.
Exactly. So there are more examples, and I just for the sake of time I wasn't going to write any, but yeah, you can generate some more explicit examples both on the real line and of the complex numbers of things that are not derivative arrays using this Gauss-Luca thing. And so one nice thing, let me just go back. So in this example of Mel, you accounted for all of the roots of your polynomial just by looking at this very first column, right? And so it gives you no rigidity at all. You know exactly what f has to be just by looking at this first column. And the nice thing about this Gauss-Luca argument is here I actually did not account for all of the roots in the first column. I only accounted for most of them. And so this left me some degrees of freedom, but I was still able to say something, yeah, because of all this convexity stuff. And so that's why I think this gives a lot more examples. And of course, this M is somewhat arbitrary. Like there are tons of other things I could have chosen and just run the same argument. Okay, cool. Any other questions, comments, ideas?
You can also get, for this matrix, right, the column that is 1, 1, 0, that's about f prime.
Yes.
And that's quadratic, so we know its roots are lambda 1 and lambda 2, but its derivative would have a root at lambda 3, which is outside the convex hull also.
Okay, but you can make this example more robust if you want. I mean, I can do like, let's see. I can sort of pad it like this. Right, so now we're going to be dealing with a quartic polynomial, and I've accounted for 3 of the roots here. And then I can run the same argument, but I can't look at just one additional column in order to get any derivative. Yeah, okay, so maybe this particular example was not the best. Because as you say, there's an easier way to do it. But I think it would be somewhat tricky to do this example just with your variance.
Your second row is wrong.
Yeah.
My second row is wrong.
It's not a derivative.
Kevin's argument applies to the modified matrix.
Yes, thank you. Okay, and then this has to be a 0, and maybe I'll put the 1 over here. Okay, you can do something. You have to do some more padding. Right. Okay, so maybe you actually can't set this up. But I think there are examples you can set up where you can't just look at some later column and get everything. Yeah. But yeah, that's a good point, Kevin. Anything else?
It's a really beautiful argument, though. It's great.
Thanks. Yeah, so I think, so one of Mel's initial questions in his paper is, what constraints can you put on these derivative arrays? And so he gave us these sort of first few ones, these multiplicity array constraints. And I think that you can come up with another list of constraints coming from this Gauss-Luca theorem, but I haven't yet been able to write down what that would actually look like. So I think this is somewhat promising, although I haven't done it myself yet. Okay, cool. So now I want to change gear a little bit and talk about another problem that Mel raised in his initial paper, which is the extension problem. So this is kind of cute. So here's the question. So let M be a multiplicity array. So it may or may not be a derivative array. But so suppose that it's not a derivative array. Is it going to be like part of a derivative array in some sense? So is there a derivative array M prime such that M is the leftmost portion of M prime? So this is the question. And this is sort of natural. So maybe I'll go back to one of my examples earlier. So for example, let's see. Actually, I can do this on the very first slide. So the multiplicity, that's not a multiplicity array. Okay, there should be examples here. Okay, yeah, so some of these guys. So if I truncate this here, this itself will not be this will not work. Okay, there are examples of things where you can look at it and say, okay, take a derivative array and look at just the leftmost portion. This is itself not going to be a derivative array. Maybe there's stuff here. Okay, in any event, here's the question. So this is the question okay? Okay, so this is Mel's question, and then the answer.
Can you read the question out? I'm just.
Yeah. Sorry, my handwriting is atrocious. Let M be a multiplicity array. So it may or may not be a derivative array. So does there exist a different derivative array, M prime, such that M appears as the leftmost portion of M prime? Is that okay?
Yeah.
Okay. So the answer is yes, very much so, in a very strong form. And so here's the statement. So this is what I did. I think I emailed Mel about this on Monday. So and I'll write it carefully. So let lambda be lambda 1 through lambda m, an M tuple. So let this be a M tuple of distinct complex numbers. And let M be any multiplicity array that you like. So let M be a M by n plus 1 multiplicity array. Okay, then there is a polynomial f of degree at most m times n plus 1 minus 1, such that m appears as the leftmost portion of mf of lambda. So this is saying that if you give me any m tuple of complex numbers, and then you give me any multiplicity array, I can find some derivative array with respect to the same set uppercase lambda, such that our given m appears at the leftmost portion of it. Okay. So unfortunately, I have to go to a new page to write the proof. Any questions about the statement before I move on? Okay. Sorry about that. Okay, so the insight is actually this proposition of Mel that I mentioned at the very beginning. So let me go back to that. So it's this one right here, which is that if you want to know what the entries are in this derivative array, it suffices to do an expansion like this and look at which coefficients are 0 or non-zero. So that's the idea, and we'll just execute this. Okay.
Can you show me the statement again?
Yes. And if you can't read it my handwriting, I can say it again. Okay, I'm really not used to this tablet thing. Yeah, so let lambda be your M tuple of distinct complex numbers, and let big M be your multiplicity array. Then there exists some polynomial f of degree at most m times n plus 1 minus 1, such that m is the leftmost portion of the derivative array mf of lambda.
Oh yeah, thanks. That makes a lot of sense.
Okay, yeah. So this is precisely what Mel was asking. Okay, so let's do the proof. Okay, so the first thing is that if m is just the zero array, then this is easy because you can just choose f to be some generic polynomial. Then this is easy. right? Because generically, you're not going to hit any of your lambda i's as roots of f or its derivatives. So assume that this is not the case. Okay. And we're just going to do this to make sure that we get a polynomial that is actually happy at the end, that we don't end up with a zero polynomial. Okay, so by the proposition that I showed you before, it suffices to construct some f that is correct. I'll say what I mean by that. Modulo each x minus lambda I to the n plus 1 for all I. So when I say correct, I mean you're going to take f, and you're going to look at it mod x minus lambda I to the n plus 1, and you're going to ask which coefficients are 0 and non-zero.
Mm-hmm.
And as long as you have the correct pattern of 0 and non-zero coefficients, then the first n plus 1 columns of mf of lambda will look like what they need to look like. And this is precisely the content of Mel's proposition from the beginning of the talk. Okay, so now we're just going to do this. You just write it down and it works. So let's let AI be the set of j's such that mij is equal to 0. So these are the guys where we're going to want f to have a non-zero coefficient.
Mm-hmm.
And then we're going to let fi of x be equal to the sum over k in the set ai of x minus lambda I to the k. And we're going to consider this as an element of C adjoin x mod x minus lambda I to the n plus 1. Okay, so this is fine. So now we're going to let g of x be this polynomial. So we're going to take the product I running from 1 to m of x minus lambda I to the n plus 1. Okay, so this is nice. So basically we're taking all of these guys for the various i's and multiplying them together. So by the Chinese remainder theorem, and this is really doing all the work, there exists some f star, which is in C adjoin x mod g of x, such that f star is equal to fi mod x minus lambda I to the n plus 1 for all I. So this is fine. This is just because the lambda i's are all distinct. Okay, so take f to be the representative of f star with degree smaller than degree of g, which is equal to m times n plus 1.
Mm-hmm.
And this just works, right? So f will have degree at most m times n plus 1 minus 1. And it has the correct residue modulo x minus lambda I to the n plus 1 for each choice of I. And so when you form these derivative vectors with respect to the lambda i's, they'll be correct, or what we wanted, for the first n entries. And this works.
It does.
So yeah, it's very short. It fits on one page, even with my terrible handwriting. And the answer to Mel's question is yes. Okay.
Pretty cool, Noah.
Thank you. And so I won't write this, I'll just say it. So if we know that all of the lambdas are contained in some subfield k of the complex numbers, then if we do this construction, we also guarantee that all of the coefficients of f are in k. So in particular, I think when Mel wrote his paper initially, he did everything with the reals instead of the complexes. And so if you, for instance, you gave me a bunch of real numbers for the lambda i's, then I can also give you this, this f, which has all real coefficients. So for what that's worth, you can do that. And so then my question is, how much can this bound be improved? Can the bound...
Good in general, now that I see how it works.
Yeah, so I think in general it can be improved. So for m equals 1, it cannot be improved, right? For m equals 1, it just gives you n, which is what you need. But for m bigger than 1, it seems like you should be able to improve it. Maybe using the fact that you have a multiplicity matrix, and so you can't have too many 1s that are far to the left, for instance. And so another thing here, so here there's a coefficient of 1 in front of all of these x minus lambda I to the k terms. I also could have chosen any other non-zero value. And so it seems feasible that if you take like generic choices of coefficients here, maybe sometimes you'll be able to take f to have degrees smaller than this bound.
That makes sense.
It does make sense, but I don't know how to do it. So I think it would be interesting to improve this bound. And in particular, I think it should be true that there is a bound which depends only on n, not on m. And this is just because all but at most, like, I don't know, some constant depending on n, many of the rows have to be all zeros. And then you can just kind of ignore these if you choose these coefficients generically. Okay, so I think you can always take this to be a most like n squared or constant times n squared. Yeah, okay, so this was just sort of a brief side remark because it answered one of Mel's questions. So if there are no objections, yeah. Oh, I thought I saw someone unmute. Okay, I will plow ahead if there are no objections.
Do you have any computational evidence for how strong the bounds can be improved?
Oh, no, I have no idea. Maybe someone could try this. I mean, this argument feels sort of wasteful. I think that if you're careful, you can define G a little bit more economically, basically by reducing some of these exponents. Yeah, but I'm not sure how much. I don't know. It's also possible that there will be some particular choices of M and the tuple lambda for which this bound is essentially tight. That would be very interesting.
That would be my guess.
But yeah, it would be nice to characterize those as well. Yeah, computational evidence would be great. I don't know how to do it myself. I can't code. Okay. Oops. Yeah. Okay. So that was sort of a side remark. And now I want to talk for a little while about one last problem, which sort of arose out of a theorem of Mel, but was not one of the questions he posed. And this I'll call equivalence of M tuples. So here's the definition. So for lambda, a M tuple of distinct complex numbers will define the following. So we'll let curly M of lambda be the set of all matrices therefore that appear as MF of lambda. So we're going to look at all of the polynomials F, and for each one, we're going to look at MF of lambda and say that this is like a derivative matrix that we're going to associate with lambda. So, and then we're going to say that lambda is equivalent to lambda prime if their curly m's are the same. So I think this is a very natural definition. So we'll say here lambda and lambda prime are equivalent. Okay, and so then the question is, what are the equivalence classes? So problem, determine the equivalence classes. And so there, again, this is really implicit in Mel's paper, and he has a proposition which gives a very good partial answer.
2 points. All 2 points are equivalent.
Sorry, what's that? Okay. So let lambda and lambda prime be M tuples such that either lambda prime is equal to A lambda plus B, or lambda prime is equal to A lambda bar plus B. So this is for A and B complex numbers, and A non-zero. And so here, when I write like lambda prime is A lambda plus B, I just mean that lambda prime sub I is A lambda I plus B. And then for the second thing, I'm taking complex conjugates. So then these are equivalent. Okay, and so the proof, okay, sorry, I have to go to the next page again. Maybe I can squeeze it in. Okay, so suppose M is equal to MF of lambda. Then I'm just going to write down a polynomial that gives the same matrix M, but measured with respect to lambda prime. So then, oops, M is equal to mg of lambda prime for g of x is equal to f of x minus b over a. And this is for the first case. This is for lambda prime equals a lambda plus b. Or I'll leave it at that, actually. So it's this for the first case, which is this. And then I'll finish the proof up here. Also, so for lambda prime being the complex conjugate, we have m is equal to mh of lambda prime for h of x is equal to f bar of x. So this first guy that I squeezed in at the bottom here is saying that if you take lambda and you take a homothetic copy, right? So you translate it and you scale it, then you can just translate and scale your polynomial f, and you'll get sort of the same pattern of the zeros, of the derivatives. And then the second part up here in the box is just saying that if you take a complex conjugate of your tuple lambda, then you can also just take complex conjugates of all the coefficients of your polynomial. And these just work. And that this works just follows from an application of the chain rule. Okay, so sorry, that's a little bit messy. But basically, what this is telling us, the conclusion, is that homothetic M tuples are equivalent. And so here, I'm talking about translations, rotations, dilations, and reflections. So the reflection is coming from complex conjugation. So this is very nice, and this tells us that our equivalence classes are at least reasonably big. And then the question is this the full extent of the equivalence classes? So are M tuples equivalent if and only if they're homothetic?
Hey, you can answer that without thinking very much, right?
Okay.
Just in terms of sizes.
So sorry, sorry, what do you mean?
They're parameter counts. The homotheties don't, the family of homotheties is a small family, okay? There are very few parameters, whereas the set of all tuples has many parameters.
Right.
And there's going to be a sort of generic situation here. The number of equivalence classes. Oh, wait. No, sorry, my mistake. Because
the problem is that there's countably many of these multiplicity matrices.
That's right. They're infinitely many, and so they might in theory divide things into. Okay, right, correct.
Yeah, this
so
is
that,
the problem. So
if you bounded the sizes, then you'd certainly have a generic situation which was gathering a lot of things into it. But as it is, no. If you're allowing arbitrary sizes, I don't see that that's true. My mistake.
Right, it's very hard. Right. So another way of thinking about this is, let's say I give you a multiplicity array M. And then I can ask you, for which tuples lambda is this a derivative array? And so this splits all of the M tuples lambda into yeses and nos, right? And then you can do this for all of the multiplicity arrays M, of which there's countably many. And we say that two tuples are going to be equivalent if they agree, like either both yes or both no, for each of these matrices. And yeah, and as Moshe, or I guess the other person on Moshe's Zoom said, I don't know which one of you is which, since there's countably many of these constraints, and there's only like a continuum many of these tuples, yeah, we can't say much. Yeah, so this is the problem, and I'm really not sure. Is this all? I'm really not sure what the answer to this should be. I think I have maybe some very tentative conjectures, which I'll mention in a couple of minutes at the end. But I think this is an interesting question. Okay, so let me give you a sort of motivating example before I prove the next theorem, which is a partial result towards this question. So here's an example. This is due to Konyagin and to me, and this is answering one of Mel's questions from his paper. So let M be equal to this matrix, or this array. Then M is in this curly M of 0, 1, 2, and M is not in curly M of 0, 1, 3. So in particular, 0, 1, 2 is not equivalent. Let's write this a little more neatly, to 0, 1, 3. So what is the example? I guess I'll write proof, even though it's a little strange. So M is equal to MF of 0, 1, 2 for f of x is equal to x times x minus 2. And you can just do this by computation. Okay, and now I want to show that M is not mg of 0, 1, 3 for any g. So suppose M is equal to mg of 0, 1, 3. Then g of x has to have a root at 0 and at 3, and it's quadratic, so up to a constant, so it's c times x minus 3. But then g prime has its only root at 3/2, just by taking a derivative. But we know by looking at the second row of M that g prime is supposed to have a root at 1. And so this shows that M cannot be mg of 0, 1, 3 for any choice of g. Because the first column really forces g to have this special form where we've accounted for all of the roots, but then we can just read off what all the derivatives are supposed to be.
So Noah, you're taking this set lambda to be with that order, right?
Yeah, so I'm not taking sets. So Mel talked about sets in his initial paper, but I think you really want to talk about ordered tuples. So I've been pretty careful about that this whole time. So there is also this question where you don't care about the order of the tuple, and then it gets a little more complicated. I'm not sure if that's more or less interesting, but I just found that this was more tractable, which is worth something, right? Other questions, comments? Okay. So this example generalizes in sort of an interesting way. Okay, and let me tell you what that is. So if lambda is a M tuple of distinct rational numbers, then it is equivalent only to its homothetic copies. Then lambda is equivalent only to its homothetic copies, as defined above. So this answers my question on the previous slide, right here, for the case where we look at a tuple where all of the numbers are like rational multiples of each other. But it doesn't solve it in general. Okay, so let me give you the proof. Unfortunately, this proof is a little bit long. It's like 2/3 of a page in my notes, but I'll try to go through it. So this is trivial if M is at most 2, right? Because if you have any, if M is 1, then of course everything is going to be equivalent to everything else. And if you have 2 things, then because we have this like homothety, we can assume that there's 0, 1, and so there's just nothing to say. So it's trivial if M is at most 2, so assume M is at least 3. Okay, so let's write lambda very explicitly as lambda 1
I think something is frozen up because I'm just seeing it. So A, and I'm not seeing it too.
Okay, maybe okay, maybe my Wi-Fi died.
No, it just
Oh,
went.
I'm
It
seeing
just,
it.
it just appeared.
Is it okay?
Yeah.
Okay, can you see
Yeah.
this? Yeah, that's fine. Okay, sorry. Okay, so we're gonna just write out very explicitly what's happening. So let's say that our big lambda is this, and then lambda prime is equal to lambda 1 prime through lambda m prime. So if we just redo our indexing, but per Kevin's comment, we re-index consistently in big lambda and big lambda prime, we may assume that the lambda i's are increasing. We may not assume that both the lambda i's and the lambda I primes are increasing, but we can assume that one of them is increasing. And we can also rescale so that lambda 1 is 0 and lambda m is 1. Okay, so we can assume this, and then so the goal is to show that lambda prime has to be homothetic to lambda. So we can also translate and dilate and I guess rotate lambda prime such that lambda prime 1 is equal to 0 and lambda prime m is equal to 1. So we can assume this, and lambda 1 prime is equal to 0 and lambda m prime is equal to 1. And so the goal is going to be to show, given this, that all of the lambda I primes have to be equal to the lambda i's. So we will show lambda I prime is equal to lambda I for all i's between 2 and m minus 1. Okay, great. So how do we do this? So we know that the lambda i's are all rational. So we're going to write lambda I is equal to a over b, where a and b are natural numbers. And you can choose them to be relatively prime. It doesn't really matter. And note that b is at least 2, right? Because lambda I is strictly between 0 and 1. Okay, so now we just define a polynomial. So let f of x be equal to x to the b minus x to the b minus 1. And we're going to consider its derivative vectors. So, okay, what is mf of 0? So this is going to be b minus 1, b minus 2, down to 1, and then we'll have 2 zeros at the end. So this is just by taking derivatives, right? Or by using Mel's proposition from before, which is very useful. So this is really just a computation. For c between 1 and b, sorry, I think we want, yeah, this is good. We have mf of c over b is equal to this. So it's all zeros except for 1, 1, which is in the b minus c position. So if you just like take derivatives of f, you take derivatives of f, and at each point you find that all but one of the roots are 0, and then the last one is at something of this form, c over b. And you just write down what it is. This is easy, so I'm not going to do it. And then also, mf of lambda is the 0 vector for all other lambda. Okay, so this is sort of the key property here. So, okay, so we know that mf of lambda, by definition, is contained in this curly m of lambda. So we assume that lambda prime is equivalent to lambda. So there exists some g such that mf of lambda is equal to mg of lambda prime. Okay, so let me write down what this matrix actually looks like. So mf of lambda is equal to this. So 0, we have a b minus 1, b minus 2. I'll keep going. Then we have a bunch of question marks. And then in this last row, we have a 1 and then a bunch of zeros. Okay, what's important is that in this first column here, we have accounted, so to speak, for all of the roots of f. So likewise, if we know that this m, mf of lambda, is also equal to mg of lambda prime, then we can just read off what the roots of g are. So g of x is equal to x to the x to the b minus 1 times x minus 1 up to a constant, because we know that g, because here we're using the fact that lambda 1 prime is equal to lambda 1 is equal to 0, and lambda m prime is equal to lambda m is equal to 1, right? So we know that this is equal to mg of lambda prime, right? And so using this, we can just read off the roots of g using this first column, right? So we know that all but one of the roots have to be from lambda prime 1, and the last root has to be at lambda prime m, right? And just plugging in what these are, we get that g has to have this form. So in fact, this is equal to f. Okay, and this is up to a constant. I don't care about the constant. Okay, but now let's look at what happens in the row for lambda I. So the lambda I row is 0, 0, and then we have this 1, 1. And so we know that that's what this row is. But then this is also equal to the lambda prime I row. It's equal to this. But recall our characterization of these derivative vectors. The only way you could get a derivative vector which had all zeros except for 1, 1 in a specific position was if the lambda you chose was of this same form. And so this implies that lambda I prime has to be equal to lambda I, because otherwise this lambda I row would not be correct for mg of lambda prime. But this is precisely what we want, because this forces lambda prime to be equal to lambda. And
it would seem to me that at least you should be able to imitate this line of reasoning for lambdas which are radicals by using a two terms, but where the binomial is not, not x to the b minus x to the b minus 1, but x to the b, x to the n minus x to the k, something like that.
Yeah, so there's going to be some distinction here between things that are algebraically dependent and things that are algebraically independent. I think
it's more narrow than algebraic dependence. Algebraic dependence can get very complicated, but here your arguments are going to be able to work only when they're very, very particular types of dependence, I think.
Right. Yeah. So certainly, I think, as you say, this can be sort of easily extended a little bit, but not so easily extended a lot. Yeah. I'm not entirely sure how far this can go. Radicals. Why do you say just radicals?
I was just thinking about the binomials when you take the x to the n minus x to the k and look at the derivatives and they're zeros.
Right. You want
You're
x
going
to the n minus x to the k.
Right.
Yeah.
It takes the derivatives. You're going to get x to the n minus j times,
this is still just going to give us rationals, right?
No, the zeros are going to appear, hold on.
They're still going to be rational.
For some reason, I'm convinced you're wrong, but I'm a little too tired to do it in my head at the moment.
Okay, I mean,
sure.
So this then f to the j of x will be equal to, let's see.
No, you get a factor which is x to the n minus k minus 1. You have to extract the roots.
I see what you mean.
I mean, put in a coefficient there, x to the n minus ax to the k. You'll see it very obviously.
Right. I see what you mean. Okay.
Yeah. You have root extraction here. At the very least, you can fit that into this framework. But I don't know if you can, I don't know how flexible it gets.
So you have to be careful though, because Right, so you're going to end up with things that look like, I don't know, x to the r minus alpha, right? But the problem is that this actually has a lot of roots. So let's say we're looking at like cube root of 2, for instance, like x cubed minus 2 is what we end up getting. How are you going to distinguish between the 3 cubed roots of 2? So I think the problem is that we have non-trivial Q automorphisms here. So there's really something special about Q.
All right, fair enough. Yep.
Yeah. So okay. In all fairness, I learned about this problem 3 days ago, and so I haven't actually had that much time to try it. And I totally believe you that something of this flavor will work, but I haven't been able to figure out what it would be. But yeah, this is a nice example, and maybe you could differentiate enough things, right? So here we only really use like one particular matrix M, or array M, but you can look at multiple different arrays if you're trying to distinguish, say, lambda and lambda prime. And so maybe you could use something like this example to distinguish everything except for these roots of unity obstructions, and then you could use some other polynomial to distinguish among the roots of unity. I totally believe that. Okay, so I just wanted to conclude with an open question, very much in the vein of what we were just talking about. So which of the following triples are equivalent? So I'm just going to write down some things, and hopefully some of you will have ideas. So 0, 1, square root of 2, 0, 1, square root of 17, 0, 1, 5 to the 1/3, 0, 1, pi, 0, 1, e. I have no idea. So here we're looking at, for instance, algebraic numbers of the same degree. Here we're looking at algebraic numbers of different degree. And here we're looking at some transcendental numbers. So
Is it obvious the last two are not equivalent?
So I'm guessing that these last two are equivalent. Somewhat surprisingly, because it kind of feels like any constraints that you can get involving 0, 1 have to be completely independent from all the constraints that you get involving the last guy, when the last guy is transcendental. And then I kind of feel like you can substitute one transcendental number for another. But I have no idea how one would actually prove this. So this is the parting question that I leave you guys with, and that's the end of what I prepared to talk about.
Great. Let's see. What can we do? Can you unshare the screen?
Yes.
Yes, we need it in a moment. Okay. Is there any comments or questions for Noah?
Great lecture.
Thank you.
Yeah, very good.
So let me just make one comment. So in the first draft of the paper I wrote, since I had been thinking about Descartes' theorem and Boudin, Fourier, and Sturm, I just used, I made everything a real number. Noah had asked me in some email about complex numbers, but then I realized I don't use real or complex numbers. It's purely algebraic, everything that I did, right? So in the most recent version of my paper, I just said, let K be a field of characteristic 0, and everything is purely algebraic, and you just do things over the field K. And for example, where Noah said when he was looking at equivalent M tuples, for the complexes, you have conjugation. But in general, you can take any automorphism of your field, and that generates an equivalence class. The thing that I thought was really interesting about your talk was the one thing or that didn't apply to arbitrary fields of characteristic 0 is when you use convexity. And,
So
and I don't know.
I'm thinking about the proof. I think that you can write down this GaussLuca theorem for any field of characteristic 0.
Yeah. So that's interesting. I mean, I know Gauss-Lucas, and and I've never thought about it except over the reals or complexes. So, and I'm actually trying to remember I remember there are lots of proofs, and the proofs that I can sort of think of are kind of algebraic, but but that I thought was really interesting, that your idea that you could use convexity here in the first place is great. And also in this last version of the paper, I had added a comment that if you try and do these things over a field of characteristic P, that's more complicated.
Yeah.
And I have no idea at the moment what would happen there. Because you don't have Taylor's theorem. You can't divide by factorials. So things get messed up with it.
And for instance, you don't even have these multiplicity array restrictions, right? Because if you have something which is a p power, it just gets killed.
Right. No. So you have to actually sort of think of what would be the characteristic P analog with these things.
Yeah.
And as you said, you've been thinking about these things for 3 or 4 days, and I have an edge on you. I've thought about them for a week and a half or so. So, and, there's only so much time in the day, and we're not on spring break yet. So,
have you had a look at the material on Birkhoff interpolation?
No, what's that?
I mean, Birkhoff interpolation is when you state restrictions on a polynomial and its derivatives, and not necessarily consecutive derivatives. So Taylor approximations, you use information on a point and its successive derivatives. A Lagrange interpolation, you just use the function itself at different points. So Birkhoff interpolation is when you sort of sample at a number of different points, a number of different derivatives, but not necessarily consecutive. And there's a question there about when do you get a unique solution? When do you get I mean, I think for us, what we'd really want is a non-unique solution, so as to ensure we're looking at homogeneous systems really, and we want a non-trivial solution. So I think that's what they call in that particular field non-poised conditions. So there's a condition of Polya. I'm still trying to figure out exactly how well it applies here, if at all. But there is material that's awfully close to this question, and they had under the heading of Birkhoff interpolation.
Okay. Yeah. So it's interesting. So let's say that I give you some multiplicity array M, and I give you a tuple lambda, and then I ask, is it the case that this M is a derivative array for this lambda? So answering this question, if I want to answer this question, I can just set up, okay, let's write out the polynomial with coefficients, and then I get a bunch of linear combinations of the coefficients, which have to be either 0 or non-zero.
Right. So getting zeros is classical for linear algebra. Getting something not equal to 0, that's a little trickier. Yeah. It's not a standard question in linear algebra.
Right. And the point here, though, is that everything is linear, which at least helps us. Yeah, I agree. It seems a bit tricky. I suspect that the real algebraic geometry people might just know this, but I don't know any of them.
Any other questions or comments? So I thought it was a really great talk also. It's a lot of interesting things. And I'm glad you were on spring break this weekend.
Yeah. I had some computations to report that are in line with what we were just saying. Go ahead and share my screen, right? So I was looking at the counting problem where you just fix M and N and how many of those are actually derivative arrays. And for one dimension, of course, it all depends on where the zeros are. So 2 to the n straight counting. And then it's just a computational problem, right? So for a 2 by n plus 1s, there's only so many possibilities. And just grinding through it all for small n's led to this formula. Right? And looking more carefully at which one.
Sorry, so what is A2 of n again?
So A2 of n is the number of 2 by n plus 1 derivative arrays.
Okay. Okay. Without any, just the definition of this, just the definition. No question, right. And then you're asking how many of these come from a polynomial?
No. So the derivative arrays come from a polynomial by definition, right?
You're allowing any lambda. You're letting lambda change, for instance.
Yeah, well, I'm only talking about 2 rows, so lambda doesn't matter. Right?
Okay,
So
but in general, you might, yeah.
Yeah. Well, in general, I don't know what the right thing to count is. Maybe we need to introduce lambda, but I don't get past 2 rows anyway. Yeah, so looking more carefully, I can kind of figure out what's going on with that. It looks like a 2 by n+1 multiplicity array. So these are the arrays that have the row condition and the column condition that Mel talked about last week. It's actually a derivative array if and only if for the last k columns, we have at most k-1 non-zero entries. And the explanation for that is what Noah and Moshe were just saying, right? Each non-zero entry gives us an equation. If we just have k equations and we have k unknowns, then probably that's going to force all the coefficients to be 0, which violates the non-zero parts. And it looks like for 2, you can work out what those equations are, and it does seem that they are non-singular in all of their combinations. So I don't have a proof, but that's kind of an explanation for why we would expect this kind of a condition. And as far as I know, this conjecture matches with all of my data, which doesn't go up to n being 20. It's only up to 12 for some, maybe 13 by now. But it seems to be the whole game, right? Once you force there to not be very many non-zero entries off to the right, then you're good. So there we are, conjectures and suggestions, but no proofs from me.
What's the answer to your question at the bottom of the page?
Oh, well, let's see. So 1, 2, 3, 4, 5, 6 non-zero places, and degree 1, degree 2, degree 3, 4, 5. So that's 6 coefficients, 6 equations. That forces all of the a's to be 0. It is not a derivative array.
Why is there a 1 on the end of the second row?
Oh,
Yeah, that's not kosher.
yeah, sorry, because I was just scribbling it down at the end. While listening to Noah, I was also writing. So there we are. But in general, right? Any 2 by 6 array, which has 6 non-zero entries, is not a derivative array. And that goes out by computation truth out to n equals 10 or 11 or 12. I'm not sure where my code for this actually stopped, but
I think that would be Polya's condition for the Birkhoff interpolation. But again, I'm uncertain because I haven't really internalized that material.
yeah, you might notice I scribbled that just up in the corner as you were saying it, because that is exactly what's happening here.
So if this works, then it's definitely specific to height 2, because this example that Sergey and I came up with shows that for height 3 you do get redundancy.
Yeah, right. So I would believe that, like, if you force for an arithmetic progression of lambdas, something like this might be in the offing. But for general lambdas, it's so the lambdas are also providing degrees of freedom, right? So if you're allowed to let the lambdas float, then you've got more freedom. You can have more non-zero entries and still survive.
Right.
Other comments or questions for Noah, for Kevin, for Moshe?
Looks like a fruitful topic for further research. A lot of things going on in it.
Yeah.
Unless Polya already knew everything.
It's still fruitful for us.
So in Birkhoff interpolation, is it Birkhoff the father or Birkhoff the son?
This I don't know, but I do know that once you get to 3 rows, it gets messy, even you know, for the
Oh,
expert.
yeah.
Yeah.
So it's not that this is a well understood field in general.
Yeah, no. Once you have M equal 3, in the notation that's being used today, it's then things get interesting.
So, yeah, okay.
Yeah. And
have a
Kevin, I
question.
assume
Take it offline.
I assume you're happy to share your calculations with whoever might be interested in seeing your infinitely long list of polynomials.
Absolutely, sure. It's in Mathematica, if that's helpful. But the
When you
output
send it, when you
matrix-
send it to me, I asked for it as a PDF file. Okay. Thank you, everybody. Let's see. We actually have, it's very unusual for us to plan in advance, but I think we have the next 3 or 4 weeks of talks already
Four.
scheduled.
4 weeks.
There is a possibility of squeezing in Nathan if he ever wants to give a talk, but no pressure, Nathan, no pressure.
Yeah, I looked at the schedule, maybe like, after the next 3 or 4 weeks. I have something I'd be excited to talk about.
Good. Okay. If there's nothing else, everyone enjoy the day. Where I live, the snow was on the ground this morning and it's melted by now. So that's good.
Thanks.
Very
Take
much,
care.
Mel.
Bye, all.
Bye. Bye.